In the previous two videotapes, we discussed solving quadratic equations by factoring and by extracting roots. Now, these techniques are limited in that they don't always apply to all problems. There are quadratic equations that we can't handle by either of these two methods. Today, we're going to generalize the method of extracting roots so that it will apply to all problems. This videotape deals with solving quadratic equations by completing the square. Okay, before we get to that, let's look at an example that we can work out by taking square roots. Here is a quadratic equation, and we can solve this by extracting roots. We take square roots of both sides. On the left side, we get x plus 3, and on the right side, plus and minus the square root of 7. Okay, now we want to solve for x. We can subtract 3 from both sides of this equation. X is therefore equal to minus 3 plus or minus the square root of 7. Okay, what I've done here is to subtract 3 from both parts. Okay, x plus 3 minus 3 gives you just x over here. Now, this plus or minus the square root of 7, okay, that's one thing. We're going to subtract 3. So you can either write this as plus or minus the square root of 7 minus 3, or minus 3 plus or minus the square root of 7. Okay, either way. Now, this is the solution to the quadratic equation. There are two roots here. We have x equals minus 3 plus the square root of 7, and x equals minus 3 minus the square root of 7. This is how you interpret this. Minus 3 plus the square root of 7 and minus 3 minus the square root of 7. And these, as I mentioned before, could have been written in reverse. Plus the square root of 7 minus 3 and minus the square root of 7 minus 3. Here we have the solutions. Okay, now that's fine if you happen to be given something in this form. A perfect square equals, say, some number here. Now, suppose this equation had been given to you in the expanded form. In other words, we have here x plus 3 squared, that is x plus 3 times x plus 3 equals 7. This is x plus 3 squared equals 7. But instead of getting it in this form, we got it multiplied out. Let's multiply this out using the FOIL method. We have x squared plus 3x, that's plus 6x, plus 9 equals 7. And we can go even one step further. Let's put it into standard form for a quadratic equation. That means everything on one side equals 0. We subtract 7 from both sides, and we get x squared plus 6x plus 2 equals 0. Okay, now this quadratic equation is equivalent to the top one in that they have the same solution sets. Okay, we start, if you had it in this form, and you can see right away that you can take square roots of both sides and get the solution immediately. In this form, in standard form, okay, we cannot take square roots of both sides. Okay, this is not a perfect square as it's written here, nor can we factor in this particular example. We cannot factor this over the integers. We would be looking for two numbers that multiply to 2 and add to 6, and we wouldn't be able to find them. All right, so we can't factor this over the integers if it's in this form, nor can we take square roots. Now, we see that there is a form of this that does involve a perfect square. The question is, how do you recognize a perfect square? How can you take a problem that doesn't have a perfect square and make a perfect square part of it? After all, this came from a perfect square. In this form, though, that's obscured. We cannot see that it's from a perfect square the way we can in the first line. Our object is to somehow put this into the form of a perfect square so then we can solve the problem by extracting roots. Okay, now let's look at a perfect square in general. So we have something like x plus a squared. This is, of course, x plus a times x plus a, which is x squared plus ax plus 2ax plus a squared. X plus a squared is x squared plus 2ax plus a squared. It's the first term's x squared. Outer is ax, inner is ax, so you have 2ax, and the last is a squared. Okay, let's look at some different values of a. let's say we had x minus 3 squared. X minus 3 squared, or x minus 3 times x minus 3 gives us x squared minus 3x minus 6x plus 9. If you had x plus 4 squared, this would be x plus 4 times x plus 4, x squared plus 4x, that's plus 8x plus 16, x minus 5 squared, x minus 5 times x minus 5, that's x squared minus 10x plus 25, x, say, plus 6 squared, x plus 6 times x plus 6, or x squared plus 12x plus 36. We're looking to see if there's some kind of pattern that these perfect squares have in common. Okay, let's look at the x minus 3 squared. Okay, we see that the coefficient here of the first degree term, that is the coefficient of x, minus 6, is this number doubled. Here, the coefficient of the first degree term, which in this case is 8, is this number doubled. The coefficient here, minus 10, is this number doubled. And the coefficient here, plus 12, is this number doubled. If we look at the general case, the x plus a squared, let me just put this right above this so you can match it up. You have x plus a squared, x plus a times x plus a, x squared plus 2ax plus a squared. And of course, in the general case, when you have x plus a squared, we notice that the coefficient of the first degree term, when it's expanded, the coefficient of the first degree, or the x term here, 2a, is this number doubled. Okay, and it always works that way. This is this number doubled. Now, if it's a negative number, for example, minus 3, you get minus 6. 2 times the minus 3 is minus 6. If it's a positive number, 4, 2 times 4 is 8. Okay, negative 2 times minus 5, that gives you minus 10. 2 times 6 gives you plus 12. Okay, the coefficient of the first degree term is double this quantity. Now let's look at the last term in the expansion in each case. In each case, what you get for the last term is this number squared. Okay, minus 3 squared is plus 9. Plus 4 squared is plus 16. It doesn't matter if it was positive or negative here. We're going to square it. It's going to come out positive. We have minus 3 squared. We have the plus 4 squared, the minus 5 squared for the 25, the plus 6 squared for the 36. And of course, in general, what we get here is a squared. So we can see a certain pattern. X plus a squared. You're always going to get first the x squared, then you're going to get this number doubled times x plus this number squared. Okay, anything in this form is a perfect square. Now, why do we want a perfect square? Because if we can recognize something as being a perfect square, for example, this is a perfect square, we can write it as x plus a squared, which will set us up for solving a problem by extracting roots. Remember, when we had it in this form, we were able to take square roots of both sides, which we did over here. Okay, if you can get it in the form of a perfect square equals a number, you can take square roots of both sides, get the square root here, and solve the equation in that way. And that's our goal in all problems, even those that are not written explicitly to start off with as a perfect square. Okay, and as I mentioned before, in this particular problem, it might have been given to you in the equivalent form, x squared plus 6x plus 2 equals 0. How do you know that there's a perfect square in there, and more important, how do you put it back into that form? Okay, let's start with x squared plus 6x plus 2 equals 0, and try to put this into the form x plus 3 squared equals 7, so that you could solve it by taking square roots. Let me put that up on the top. X squared plus 6x plus 2 equals 0. Okay, now what we're going to try to do is to match this up to what we know to be a general perfect square, that is x squared plus 2ax plus a squared. Okay, now the important thing is that we must start with lead coefficient equal to 1. We'll see in a later example if the coefficient of x squared is not equal to 1, we will divide through by that number to start. Okay, we'll get to that later on. Okay, so all I want you to have on top here is that x plus a squared is x squared plus 2ax plus a squared. We'll need that. Okay, and here's what you do. You start off by subtracting 2 from both sides of the equation. Okay, in an effort to have just x squared plus 6x equals here minus 2. We want to start with, say, x squared plus something times x. The constant is going to go over to the other side. Okay, we see this is not a perfect square as it stands. If it were a perfect square, you would have, okay, looking up over here, if it was a perfect square, this, okay, instead of having a 2 here, we would have half of this number squared. Let's look at this over here. You notice that a here is double to give the 2a. Okay, and then here we get just a squared. So there is a relationship between this number and this number. What we do is we take half of this number, that gives us a, and we square it. And if we go back over here, we see that relationship in all of the examples. See, we're approaching it from the point of view of, say, x minus 3 squared. So we said that we double this number to get this, and then we square it to get this. Okay? But if we were just looking on the right-hand side, so how do we recognize a perfect square? There is a certain relationship. Okay? In each case, the last number is half of this coefficient squared. Half the coefficient of the first degree term squared. See, half of minus 6, that's minus 3. Of course, it's the same number that we had here. But half of the coefficient here is minus 3 squared is 9. Half of the plus 8, 4 squared is 16. Half of the minus 10, it's minus 5 squared is 25. Half of the 12, that's 6 squared is 36. So we'll know we have a perfect square if the constant is the square of half of this number. Okay? And we see this in the general form here. The constant, which is the a squared, it's half of the 2a. That gives you a and squared. The constant to have a perfect square should be half of this coefficient squared. Back over here. We want to match this up. We would like to have a constant here, which is half of this number squared. Now, half of 6 is 3. Half of plus 6, half of plus 6 is plus 3. We would like to have a plus 9 here. Okay? What we're going to do is to add 9 to both sides in an effort to do this. I'll do it again in a few moments, actually matching it up to the formula. But those of you, some of you may be able to see it right away. I am taking half of the coefficient of x, half of 6, that's 3, squaring it, getting 9, adding it to both sides. Why am I doing this? Because this gives me x squared plus 6x plus 9 on the left, which happens to be a perfect square. It satisfies the condition that the constant is half of this number squared. Okay, and of course on the right you get minus 2 plus 9, which is 7. Now this is x plus 3 squared equals 7. And you would then solve this, of course, by taking square roots of both sides. X plus 3 is plus or minus the square root of 7. And then finally subtracting 3 from both sides, which we did earlier, we get minus 3 plus or minus the square root of 7. And here we have the two solutions. We started from this point, we took square roots, we got it. The thing is, we were able here to start from the expanded form, okay, in which there was no perfect square, immediately obvious here, and to put a perfect square into the problem. Now, the only thing we did was to add a number to both sides. Add the same number to both sides of an equation, which of course you can do. If you have an equation, you are allowed to add the same quantity to both sides. Now, we just don't add any old number, okay? I didn't add 942 or something like that. Why did I add this number? The number I add to both sides is a number which, when added here, will give me a perfect square. That's the whole idea. You want to have a perfect square on the left side so that you can take square roots and solve the problem by extracting roots. Okay, now, to get a perfect square, you must have something in this form. You must have an x squared term, a constant times x, plus a constant which is half of this number squared. We see this in the general form here. Take half of the coefficient of the first degree term, half of 2a, that's a, square it and add it on. If it helps you, it's perfectly okay to go over and to match it all up and to say, look, we have x squared plus 6x plus 2 equals 0. We take away 2 from both sides. We get x squared plus 6x is equal to minus 2. And we would like x squared plus 6x to look like x squared plus 2ax plus a squared. Okay? We want it to be a perfect square. A perfect square is something in this form, x squared plus 2ax plus a squared. What we've got here on the left-hand side is x squared plus 6x. We want the left-hand side to be a perfect square. It should look like this. Okay? So you can actually say, well, 2a has got to be equal to 6. 2a has to be 6. From that, you can see a is 3. A squared is therefore 9. Okay, if it helps you to go through this kind of procedure, by all means do it. Okay, all I am doing, okay, is still taking half of this number, 3, and squaring it 9, and saying that's how much I am off from a perfect square. In other words, what's missing here to make this a perfect square is a plus 9. This is missing. This is what we wish we had there. If it had been x squared plus 6x plus 9 instead of x squared plus 6x, then I'd have a perfect square. That's what I'm off by. To figure out how much you're off by, you have the coefficient of the first degree term. You get a 3. Square, that's where I got the 9. And if you want a mechanical way of doing it, you can set the coefficient of the first degree term equal to 2a, halve it, in other words, that means find a, and then square it. Okay, once you have found what you're missing, that is what you add to both sides. In other words, I wish I had the 9 here. So you add the 9 to both sides. You can't just add it on one side. You add it to both sides. This gives you then a perfect square on the left, a number on the right. The number on the right does not have to be a perfect square. You then take square roots of both sides. If the number on the right is not a perfect square, you will wind up with a square root here. So it's not a rational number. That's perfectly okay. And you finish the problem. Okay, let's try some more examples. Let's try the example x squared minus 8x minus 5 equals 0. X squared minus 8x minus 5 equals 0. Now, when faced with a quadratic equation like this in standard form, your first thoughts might be to solve this by the method of factoring, but we cannot factor this equation over the integers. We would be looking for two integers which multiply to minus 5 and add to minus 8, and we can't find them. Okay, we wouldn't be able to find two integers multiplying to minus 5 and adding to minus 8. Okay, so we're not going to be able to do that. Okay, so what we're going to do is to try to do this by the method of completing the square. It's not, right now it's not a candidate for taking square roots either. The left-hand side is not a perfect square. We're going to try to complete the square on the left-hand side, make a perfect square, and then solve the problem by the method of square roots. The first thing we do is get rid of the constant. Okay, this is not a perfect square, by the way, as it stands now, because this number is not half of this squared. Half of minus 8 is minus 4. Squared, it's 16. This is not 16. If it's not 16, get rid of it. Move it over to the other side, and we'll start the problem. X squared minus 8x is equal to 5. Okay, and as I mentioned, what we want is a perfect square on the left. For this to be a perfect square, we need half of this number squared added to both sides. Now, half of minus 8 is minus 4. Squared is 16. We add 16 to both sides. If you wanted to solve this, you could say 2a, as we did before, is minus 8. Half of it, that is a, is minus 4. Square it, you get plus 16. That's what is to be added to both sides. Okay, you can always work it out by letting 2a be the coefficient of the first degree term and figuring out what a squared is, and a squared is what you add to both sides. Having done this, we get x squared minus 8x plus 16 is equal to 21. Okay. On the left-hand side now, we do have a perfect square. That's why we did it. It's x minus 4 squared is equal to 21 here. This is x squared minus 8x plus 16. We do have a perfect square. We can now solve this by taking square roots. X minus 4 is plus or minus the square root of 21. We took square roots of both sides. We now add 4 to both sides. When you add 4 here, the minus 4 goes, you just get x. When you add 4 here, you get 4 plus and minus the square root of 21. We have here two real solutions to this problem. Now, as you know, in a quadratic equation, you should always check your solutions. Okay, it gets a little complicated when your answer is irrational. The check is a little messy, but I want to go through it for you just so you can see how it works through. I'll only check one of the solutions. The other one is checked in a similar fashion. Okay, remember there are two different solutions here. X is 4 plus the square root of 21, and x is 4 minus the square root of 21. Okay, so let's check. When we're checking in the equation, x squared minus 8x minus 5 equals 0. We want to check x is equal to 4 plus the square root of 21. And then in a similar fashion, we would check 4 minus the square root of 21. Every time we see an x, we write 4 plus the square root of 21. We have 4 plus the square root of 21 squared minus 8 times 4 plus the square root of 21 minus 5 should be equal to 0. Okay, 4 plus the square root of 21 squared means 4 plus the square root of 21 times 4 plus the square root of 21. Here we have minus 8 times this minus 5 should be equal to 0. Let's square this by the FOIL technique. First squared, okay, is 16. Outer is 4 the square root of 21. Inner is 4 the square root of 21. That gives us 8 the square root of 21. Last is the square root of 21 times the square root of 21, which of course is just 21. Now, minus 8 is to be distributed through the parentheses, giving minus 32 minus 8 the square root of 21. Minus 8 times 4, and then minus 8 times the square root of 21. Minus 5 should be equal to 0. Here we notice that the plus 8 the square root of 21 and the minus 8 the square root of 21 knock each other out. What we have now is 16 plus 21, that's 37, minus 32 minus 5 minus 37, which of course comes out to be equal to 0, and it checks out. And in a similar fashion, you would also check x equals 4 minus the square root of 21. Okay, check this the same way. Okay, let's try another example. X squared plus 4x plus 6 equals 0. Okay, the first thing you notice is that, well, we can't solve this by factoring. We need two integers multiplying to 6 and adding to 4, and you're not going to be able to do that. For example, 3 and 2 multiply to 6, but they add to 5. Okay, since we can't do it that way, we look to see if this is by any chance a perfect square, and we see that it's not, because to be a perfect square, this number must be half of this number squared. We want the square of half of this number. Now, half of this number, 4, half of this number is 2, squared is 4. What we've got is a 6. Okay, so it's not a perfect square now, and since it's not, we're going to move the constant over to the other side. We'll have x squared plus 4x equals minus 6. Now we're going to add a quantity to both sides. That quantity is half of this number squared. Half of 4, that's 2. Squared, it's 4. Add 4 to both sides. Okay, and where the number 4 came from, if you don't see it this way, what I do is I set the coefficient of x, which is 4, equal to 2a, figure out what a is, and square it. That's how I get the number to add to both sides. Here I have x squared plus 4x plus 4 equals minus 2. On the left-hand side, we have a perfect square. X plus 2 squared equals minus 2. And we've done this by the method of completing the square. Unfortunately, if we try now to take square roots of both sides, we run into trouble because you cannot take the square root of a negative number. This equation has no real solutions. Not all quadratic equations have solutions. This equation has no real solutions, and it's apparent in this form. See, it wasn't obvious in the top form. But in this form, it's apparent because to have a solution, you'd have to have an x value, which we plug in here would make it a true statement. Now, if x were negative or positive, okay, or even 0 in this case, because we have 0 plus 2 would be 2, any of these events, if x is negative, well, if x were negative, positive, or 0 squared, there is no way it's going to come out to be negative 2. Okay, it can't the square of a number can't possibly be negative. There is no x value that you're going to plug in that's going to make this a true statement. Therefore, this has no real solutions. Remember, a quadratic equation has at most 2 real solutions. Okay, if the right-hand side, when you complete the square, if the right-hand side comes out to be a positive number, you will get 2 real solutions. If the right-hand side comes out to be 0, when you take square roots, you will only get 1 solution. And if the right-hand side comes out to be negative, you will get no solutions. No real solutions to this problem. Okay, let's try another example. And this time I'm going to give you an example with fractions. And when you have to complete the square, you bring fractions in. It's also an example that could be done by factoring. I want you to see it done both ways. The example we're going to work out is x squared minus 3x plus 2 is equal to 0. Now, this example can be done simply enough by the technique of factoring. Okay, we need 2 integers which multiply to 2 and add to minus 3, and the answers are minus 2 and minus 1. Okay, when you check this out, you get x squared minus x minus 2x. That's minus 3x plus 2. We have the product of 2 numbers equal to 0. Okay, so that means either this number is 0 or this number is 0, giving us x equals 1 and x equals 2 as our 2 solutions. Here I added 2 to both sides. Here I added 1 to both sides. Now, we have x squared minus 3x plus 2 equals 0. The first thing we notice is that this plus 2 is not what we need to complete the square here. We're going to have to subtract 2 from both sides. This gives us x squared minus 3x equals minus 2. What we have to do is, to complete the square, is to add half of this number squared to both sides. Okay, in a problem like this, it might help you to actually use the 2a technique. 2a is the coefficient of the first degree term. 2a is minus 3. We're looking for a squared, or that is half of that squared. Okay, the first thing we do is divide both sides by 2. We get a is minus 3 halves. Square it, we get plus 9/4. That is what is missing here. We have to add 9/4 to both sides of this equation in order to complete the square. That is, we want half of this number, which is minus 3 halves, squared. That's 9/4. Add that to both sides. I know this is not the easiest way to do this problem, but it's good practice for you. On the left side, we have x squared minus 3x plus 9/4. On the right side, we have minus 2 plus 9/4. Okay, this is a perfect square. It's x minus 3 halves squared. Okay, it's x, take away half of this number, squared. It's x squared minus 3x plus 9/4. On the right-hand side, in order to add minus 2 and 9/4, we change minus 2 into quarters. We get minus 8/4 plus 9/4 gives us 1/4. Minus 2 is minus 8/4 plus 9/4, 1/4. We now have a perfect square on the left. We take square roots of both sides. X minus 3/2 is plus and minus the square root of 1/4. Okay, we have x minus 3/2 is plus or minus the square root of 1/4. So happens in this particular problem, the right-hand side is also a perfect square, so when we take the square root, we get here plus and minus 1/2. The square root of 1/4 is 1/2 because 1/2 times 1/2 is 1/4. We now add 3/2 to both sides, giving us x equals 3/2 plus and minus the 1/2. This gives us two solutions. 3/2 plus 1/2 and 3/2 minus 1/2. Now 3/2 plus 1/2, that's 4/2, that's 2. And 3/2 minus 1/2, that's 2/2 or 1. And we get the same two solutions, of course, that we got from factoring. Okay, I don't want you to think that I've gone crazy. There is nothing. Of course, the way to do this is by the method of factoring. Okay, but I wanted to give you an example that could be done by factoring. Do it also by completing the square, because this particular problem is very interesting because of the fractions. Okay, we'll see other problems that can't be done by factoring, okay, that you have to do by completing the square that also involve the fractions. Okay, and I want to do one more example with you. It's 2x squared minus 20x minus 10 is equal to 0. Okay, what I want to warn you against is trying to, well, you could try to factor. It's not going to work out in this particular case. What I want to warn you against is trying to jump in and complete the square in this form. Our technique for completing the square was based on having 1x squared. In other words, the lead coefficient, the coefficient of x squared was plus 1. If it's not, you have to first factor out that 2 or divide both sides by 2. Divide both sides of the equation by 2. We must start off with 1x squared. Okay, so let us proceed the usual way. We can factor the 2 out, leaving us with 2 times x squared minus 10x minus 5 equals 0. That's 2x squared minus 20x minus 10 equals 0. That's okay. We can then divide both sides of this equation by 2, giving us x squared minus 10x minus 5 equals 0. Now we have the 1x squared. We can try to factor. It's not going to work. You can't find two integers that multiply to minus 5 and add to minus 10. It is not a perfect square in this form. We will add 5 to both sides. This gives us x squared minus 10x equals 5. To complete the square, we must add half of this number squared to both sides. Half of minus 10 is minus 5. Squared, it's plus 25. That must be added to both sides. When we do that, we get x squared minus 10x plus 25 equals 30. X squared, let me just rewrite that. X squared minus 10x plus 25 equals 30. On the left-hand side, we have a perfect square. It is just x minus 5 squared. In other words, if you've completed the square, what you get is x and then half of this number, quantity squared. We now take square roots of both sides. X minus 5 is plus minus the square root of 30. And we add 5 to both sides. And this gives us x is plus and minus the square root of 30 plus 5, or we usually write it the other way. It doesn't really matter. Plus 5 plus and minus the square root of 30. This gives us two solutions. 5 plus the square root of 30, 5 minus the square root of 30. And there's nothing wrong with doing it the other way. The square root of 30 plus 5 minus the square root of 30 plus 5. And here we have the two solutions to this example, and this is the end of the tape.